A silent thump echoed through the cosmos in 2015. It was the sound of two black holes colliding over 1 billion years ago, a ripple in space-time detected by the LIGO observatory. But that signal was a recent whisper in a much older story. Rewind the tape of the universe to its very first fraction of a second, to the Big Bang itself. In that unimaginable flash of creation, the fabric of reality is theorized to have shuddered, generating the very first gravitational waves. These are the primordial gravitational waves, the universe's inaugural space-time ripples. They are echoes from the moment of creation, and they carry secrets about how everything began. By the end of this journey, you will have explored 30 of the most incredible theories scientists have crafted to explain these ancient whispers. We will venture from the leading idea of cosmic inflation to wild concepts involving colliding universes and cracks in the fabric of reality. Could these ripples be the shudders of a cosmic phase transition, or the vibrations of strings thinner than an atom yet stretching across the cosmos? What would it mean if the first thing we detect is not from our universe, but from one that existed before it? Are you ready to explore the very edges of cosmic possibility? The most compelling answer begins with a whisper of quantum foam. Within the first trillionth of a trillionth of a trillionth of a second after the Big Bang, the leading theory suggests our universe underwent a transformation so violent it defies all intuition. This is cosmic inflation. Picture the universe not as a fireball, but as a speck of potential, 1 billion times smaller than a single proton. Then, in an instant so brief it has no human comparison, this speck was seized by a mysterious force field scientists call the inflaton field. It was as if reality itself found a hidden gear and slammed the accelerator to the floor. The universe did not just expand, it inflated, stretching faster than the speed of light, doubling in size over and over again in fractions of a nanosecond. In that fleeting moment, the entire observable universe grew from a subatomic point to something roughly the size of a grapefruit. But inflation did more than just stretch space, it stretched the very fabric of reality. At the quantum level, empty space is never truly empty. It is a seething, bubbling foam of virtual particles popping in and out of existence. These are quantum fluctuations, tiny wrinkles in the fields that make up reality. During inflation's frantic expansion, those microscopic wrinkles were stretched to cosmic proportions. Imagine taking a tiny crease in a deflated balloon and then inflating the balloon to the size of a city. That small crease becomes a massive, landscape-defining ridge. In the same way, those quantum wrinkles in the inflaton field were imprinted onto the fabric of space-time itself, becoming the seeds for all future structure, the blueprints for galaxies and clusters of galaxies. And just as a violently shaken blanket sends out ripples, the incredibly rapid stretching and smoothing of space during that inflationary burst would have generated powerful gravitational waves, the primordial space-time ripples we seek. For cosmologists, detecting these specific waves would be the ultimate smoking gun, a direct echo from that inflationary moment. It would be like finding the fossilized vibration of creation's first heartbeat, confirming that our universe truly did begin with this unimaginable exponential leap. But cosmic inflation is not the only contender for that first great shudder. Rewind the tape again to a moment just a fraction later, when the newborn universe was still a seething, unimaginably hot soup of fundamental forces. In those first moments, the four forces we know today, gravity, electromagnetism, and the strong and weak nuclear forces, were believed to be unified into a single super force. As the cosmos expanded and cooled, it began to settle like a red-hot piece of metal cooling into a solid. This cooling did not happen smoothly. The universe underwent sudden, violent shifts in its fundamental state, known as phase transitions. Think of water freezing into ice. At a certain critical temperature, the molecules suddenly lock into a rigid, crystalline structure. That shift releases energy and creates cracks and stresses in the ice. Now magnify that process to a cosmic scale. As the early universe cooled past certain critical temperatures, the unified force fractured. The strong nuclear force broke away from the electroweak force. Space itself may have undergone a similar sudden change in its vacuum state, the very energy of empty space. If these transitions were violent and sudden, what scientists call first-order phase transitions, the universe would not have changed state everywhere at once. Instead, bubbles of the new, lower-energy vacuum would have spontaneously formed, like the first ice crystals in supercooled water. These bubbles would then have expanded at nearly the speed of light, colliding and merging with each other. The collisions of these cosmic vacuum bubbles would have been catastrophically energetic events. Each merger would have sent powerful gravitational shockwaves rippling through the surrounding space-time, a chaotic froth of gravitational radiation. This would not be the smooth, stretched hum of inflation, but a crashing, turbulent cacophony of waves from a universe literally cracking into a new form. The signature of these waves would be different, potentially creating a background chorus of gravitational noise with a distinct frequency pattern. Finding that pattern would tell us that the universe's infancy was marked not by a smooth, exponential stretch, but by a series of violent, shattering cosmic quakes as the very laws of physics crystallized into the form we know today. The violent phase transitions of the early cosmos may have left behind more than just echoes. They could have left actual cracks in reality. This leads us to a truly mind-bending possibility for the source of those first ripples, cosmic strings. These are not strings in any ordinary sense. They are theoretical one-dimensional defects in the fabric of space-time itself, hypothesized to have formed as the universe cooled and its fundamental forces separated. Think of it like this: when water freezes into ice, the crystallization process is not perfect. Defects and cracks form within the ice's structure. In a similar way, as the cosmos underwent its dramatic phase transitions, the fabric of space-time may not have smoothed out perfectly everywhere. At certain lines, the transition could have gotten stuck, leaving behind incredibly thin, incredibly dense filaments of trapped energy. These are cosmic strings, hypothetical cracks in reality thinner than a single atom, yet potentially stretching across the entire observable universe like ghostly spaghetti. Their density is unimaginable. A single inch of a cosmic string could weigh as much as a mountain range, and they would be nearly indestructible, relics from the first moments of time that could still be vibrating today. This is where the gravitational waves come in. These strings would not sit still. They would whip and oscillate through the cosmos at fantastic speeds. They could form loops that oscillate and eventually decay, or develop kinks and cusps that snap with incredible violence. Every such motion, every vibration, every snap of a cosmic string would send out powerful gravitational ripples. Unlike a single event from the distant past, cosmic strings would be a continuous source. Since their formation in the early universe, they would have been generating gravitational waves non-stop, contributing to a permanent stochastic background hum of space-time vibrations. Detecting that hum and finding a signature within it that matches the predicted oscillations of cosmic strings would be monumental. It would prove that woven into the very fabric of our cosmos are these ancient, vibrating scars, one-dimensional fossils from the universe's first and most dramatic growing pains. It would mean our reality is not perfectly smooth but subtly cracked, and those cracks are still singing the song of their creation. Yet another possibility for those first ripples does not even originate within our universe. To explore it, we must step into the realm of string theory and a breathtaking concept known as the Brane world. In this view, the three-dimensional space we inhabit is not all there is. Our entire universe could be a single three-dimensional membrane, or brane for short, floating within a higher dimensional space called the bulk. Think of our universe not as an isolated bubble, but as a single, impossibly vast sheet of paper drifting in a cosmic wind. Now imagine another such sheet, another entire universe on its own Brane, also floating in that same higher dimensional void. According to the colliding Brane scenario, the Big Bang, the very beginning of everything we know, was not a singular point of creation from nothing. It was a cataclysmic event, a collision. Our Brane and another one moving through the bulk smashed into each other. The energy of that unimaginable impact transferred entirely into our three-dimensional membrane, became the hot, dense seed of our cosmos. It was the ultimate cosmic drum strike. Now consider the aftermath of such a collision. When you strike a massive gong, the vibrations ring out for a long, long time. The collision of two universe-sized branes would have done the same thing on a scale beyond comprehension. It would have set our entire newborn reality ringing with gravitational waves. These would not be the subtle quantum whispers stretched by inflation, but titanic, coherent waves born from a single, universe-defining crash. The signature of these waves would be profoundly different. Scientists speculate they could create a distinct, non-random pattern in the cosmic microwave background, or manifest as a dominant hum at very specific frequencies in the gravitational wave spectrum. Finding that signature would be evidence of something almost unbelievable, that our universe has a sibling, another Brane that once touched ours and set everything in motion. It would mean the Big Bang was not a beginning, but an echo, a rebound from a collision in a higher dimensional space we cannot see. The first space-time ripples we detect could literally be the ringing of that impact, the fading vibration from the moment our universe was born from a kiss with another. The colliding Brane idea leads directly to a refined and elegant alternative to cosmic inflation, known as the ekpyrotic universe. Ekpyrosis is a word from ancient Greek philosophy meaning conflagration or out of fire. But in this cosmological model, the story begins not with fire but with cold, empty stillness. Picture two immense parallel universes, each a three-dimensional Brane, existing in a vast, higher dimensional space. They are not colliding randomly, but are drawn together slowly, almost gently, by the invisible threads of gravity acting across the bulk. In this model, our universe did not start as a hot, dense singularity. It began in a cold, contracted, and nearly featureless state. The Big Bang, then, was not an explosion from a point, but the moment of impact and rebound as these two Branes finally touched. The energy of that collision flooded our Brane, heating it instantaneously and initiating the expansion we see today. It was less a violent explosion and more like two enormous cosmic symbols coming together to create a single, resonant note that became our entire cosmos. This fundamental difference in the starting conditions, cold and smooth versus hot and chaotic, has a profound consequence for the first gravitational waves. In the inflationary picture, the universe is stretched so rapidly that quantum jitters are magnified into massive space-time ripples. But in the ekpyrotic scenario, the pre-bang phase is long, slow, and smooth. There is no period of frantic, faster-than-light stretching to amplify those quantum tremors. Therefore, the gravitational waves generated by the Brane collision itself are predicted to be far, far fainter. The spectrum of these primordial ripples would be almost undetectably quiet compared to the loud signal inflation might produce. For scientists, this is not a drawback, it is a critical clue. The search for the universe's first space-time ripples becomes a way to listen for the signature of our own origin story. A loud, clear detection would point powerfully toward a violent inflationary beginning. But if the searches come up empty, if that primordial gravitational wave background is found to be exceptionally quiet or absent, it could be a major victory for the ekpyrotic model and the colliding Brane idea. The silence itself would be a message telling us our universe was born not from a chaotic quantum leap, but from a structured, almost graceful collision in a hidden dimensional sea. The idea of a universe born from a collision hints at something even more profound, a cosmos that existed before time as we know it. This is the heart of the pre-Big Bang scenario, a theory that pushes speculation to its absolute limit. It asks us to consider that our Big Bang was not a beginning but a turning point, a cosmic rebound. In this model, rooted in the complexities of string theory, our universe is the child of a previous one. That ancestor universe was not static, it was following its own cosmic destiny, likely contracting under the relentless pull of gravity. Picture that prior cosmos not as a mirror of our own, but as a vast expanse slowly collapsing in on itself over eons, galaxies drawing closer, space itself shrinking. As it contracted, the density and energy would have soared to impossible levels. In that final, frantic squeeze, the fabric of that dying reality would have been churned into a storm of unimaginable violence. Such a collapse would not have been silent. The immense gravitational forces, the shearing and crushing of space-time itself, would have generated a deafening roar of gravitational waves, a final, desperate signal from a universe heading toward its own end. Then, according to the theory, came the bounce. Instead of collapsing into an infinite singularity of nothingness, the laws of physics, as described by string theory, might have provided a cosmic reprieve. The contraction reached a limit and reversed, like a spring compressed to its absolute limit and then released. That rebound is what we call the Big Bang, the moment our expanding universe was born. But here is the crucial twist: those gravitational waves generated in the death throes of the previous universe would not have been erased. They would have been carried through the bounce, amplified by the violent transition, and imprinted onto the newborn fabric of our own reality. This means the primordial gravitational waves we are searching for might not be the first vibrations of our universe at all. They could be the last vibrations of another. They would be a ghostly inheritance, an echo from a cosmos that has completely vanished, its only remaining trace a faint tremor in our space-time. Detecting such a signal would be the ultimate archaeological find, proof that existence is cyclical, that our universe is just one chapter in an endless book of cosmic death and rebirth. It would mean that the first thing we hear from the dawn of time is actually a farewell from a world we can never otherwise know. But to understand the true chaos of that first moment, we must shrink our perspective to an almost meaningless scale. We must journey down to the Planck length, a distance so inconceivably small that our laws of physics, our very concepts of space and time, completely break down. This is the realm of quantum gravity, and here the smooth fabric of space-time we imagine dissolves into something far stranger, a seething, turbulent quantum foam. Picture the surface of a violently boiling pot, but instead of water, it is reality itself that is bubbling. At this scale, space is not continuous. It is a chaotic froth where the geometry of the universe fluctuates wildly. Tiny wormholes spontaneously form and pinch shut in an instant. Virtual black holes, pairs of particles and antiparticles borrowing energy from the vacuum, pop into existence and then annihilate each other before they can be seen. In this frenzied sea, the very notions of before and after, of here and there, lose all meaning. The cosmos is a probabilistic storm. Now, rewind our universe to its absolute beginning, when the entire cosmos was compressed into a volume smaller than a single atom. At that instant, the entire universe was the Planck scale. All of existence was this quantum gravity foam. The smooth expansion we talk about in later moments did not exist here. There was only this primeval, churning chaos of space-time itself. Within that foam, every microscopic event, every virtual black hole evaporation, every wormhole fluctuation was a tiny gravitational disturbance. Each one sent out a minuscule ripple in the fabric of a reality that was all ripple and no fabric. Then, in a flash, the universe began to expand, and as it expanded, it did something remarkable. It froze those microscopic tremors in place. Like a pot of boiling water suddenly flash-frozen, the violent bubbles and churns of the quantum foam were locked into the stretching geometry of the growing cosmos. Those random, chaotic fluctuations at the Planck scale were stretched to macroscopic sizes, becoming the seeds for the first gravitational waves. This theory suggests the primordial waves we seek are not the product of a single, elegant mechanism like inflation or a collision, but are instead the amplified imprint of fundamental randomness. They are the fossilized frenzy of a universe being born from pure quantum chaos. If this is true, then the large-scale structure of our cosmos, the distribution of galaxies, and even the gravitational wave background carries the indelible signature of a time when space itself was a foaming, probabilistic sea. It would mean that at its heart, the universe is not just governed by quantum mechanics, it was born from it in its most wild and untamed form. That quantum foam of the early universe was a place of unimaginable density. Within that seething chaos, gravity itself could have pulled off a remarkable trick, creating black holes not from dying stars, but from the raw pressure of creation itself. These are primordial black holes, and their existence is one of the most compelling and eerie possibilities for the source of those first space-time ripples. To understand them, forget about supernovas and collapsing stellar cores. Picture instead the universe in its first second, a nearly uniform but incredibly dense and hot soup. Yet, even in that uniformity, there would have been tiny variations in density, the same quantum fluctuations we discussed earlier. In some regions, the density might have been just a fraction higher than in others. In the extreme conditions of the infant cosmos, that tiny overdensity could have been all it took. If a region of space was dense enough, its own gravity could have overcome the outward pressure of the expanding universe and caused it to collapse directly into a black hole. This would not be a slow stellar death, but an instantaneous birth, a knot of space-time tying itself off from the rest of reality in the very first moments. These primordial black holes could have formed with a staggering range of masses, from microscopic specks weighing less than a mountain to colossal entities with the mass of thousands of suns. Their formation would have been a violent, sudden event. As a region of that primordial plasma pinched off and collapsed, the rapid, asymmetric crunch would have sent powerful gravitational waves ringing outward. Think of it like a droplet of water forming and detaching from a faucet, but here the droplet is a region of space-time itself, and the plink as it separates is a burst of gravitational radiation. Now imagine not just one, but countless such events happening across the newborn cosmos, a universe-wide popping of gravitational bubbles. Each birth would contribute its own unique ripple to the growing chorus. But the story does not end there. The early universe, filled with these newly minted black holes, would have been a crowded and dynamic place. They would have moved through the dense plasma, interacting, orbiting, and colliding with each other. Mergers between primordial black holes would have been common, and each merger would have been another catastrophic source of gravitational waves, just like the black hole collisions LIGO detects today, but occurring in the cosmic dawn rather than the cosmic afternoon. This means the primordial gravitational wave background could carry a double signature, a layered history. One layer would be the sharp, distinct chirps from countless individual black hole births and mergers, now blurred by time into a continuous hum. The other would be a specific statistical pattern, a fingerprint in the frequencies of that hum that points to a universe once teeming with black holes from the very start. Finding that fingerprint would revolutionize our understanding of dark matter, as some scientists speculate these ancient black holes could be its hidden form, and it would tell us that the first structures to form after the Big Bang were not stars or galaxies, but dark, gravitational pits, stitching the fabric of space-time with their violent lives and dramatic deaths. From the violent births of primordial black holes, we turn to a possibility far more subtle, yet just as profound. It involves a particle that has never been seen, a field that permeates all of space, and the chance that the universe's first ripples are not a shout but a gentle hum from the dark. This is the theory of the action field. Actions are hypothetical particles born from a solution to one of physics' most puzzling problems, the strong CP problem in quantum chromodynamics. You do not need to understand the details of that problem to grasp the wonder of the action. What matters is this: to fix a tiny asymmetry in the laws governing nuclear forces, theorists propose the existence of an entirely new fundamental field that fills the cosmos, the action field. And this field comes with a particle, the axion, which is incredibly lightweight, potentially 1 trillion times lighter than an electron, and extremely shy, barely interacting with ordinary matter. This makes axions a prime candidate for the universe's missing mass, for dark matter itself. Here is where the story connects to our first gravitational waves. In the hot, dense furnace of the early universe, the axion field would have been frozen in a high-energy state, like a pencil balanced perfectly on its tip. But as the cosmos expanded and cooled, it crossed a critical temperature. At that moment, the field became unstable. It had to relax, to roll down to its lowest energy state, its true vacuum. But which direction would it roll? The field's potential is like a vast, gently sloped wine bottle rack with a central dip. As it cooled, the field at every point in space had to choose a random direction to roll toward the bottom. This process did not happen smoothly everywhere at once. Different regions of space would have chosen slightly different final values for the field, creating a cosmic patchwork. As the field settled into its minimum, it did not just stop, it overshot. It began to oscillate back and forth around that lowest point. Picture the entire universe filled with a substance that is suddenly, coherently vibrating. These are not vibrations in air, but oscillations in a fundamental field that is tied to the fabric of space-time itself. And a coherently oscillating field of this magnitude is not silent. The rhythmic, large-scale sloshing of the axion field would have acted as a tremendous gravitational engine. It would have pumped energy directly into the fabric of reality, generating a background of gravitational waves with a very specific telltale signature. Unlike the broad spectrum from inflation or the chaotic noise from phase transitions, the waves from axion oscillations would be concentrated around a particular frequency, like a single, sustained note from a cosmic tuning fork. The frequency of that note is directly tied to the mass of the axion particle. Detecting this specific gravitational wave signal would therefore accomplish two extraordinary things at once. First, it would provide direct evidence for the universe's first space-time ripples, a monumental discovery in itself. Second, and perhaps even more revolutionary, it would reveal the identity and properties of dark matter, solving one of the greatest mysteries in all of science. It would tell us that the invisible substance holding galaxies together is not a sea of exotic particles, but a universe filled with the gentle, coherent vibration of an ancient field that began its eternal dance in the cosmos's first moments. The silent dark would suddenly have a voice, and its song would be a gravitational hum from the dawn of time. The axion field's gentle hum offers one pathway from quantum fields to gravitational waves, but it was not the only actor on the inflationary stage. A more subtle and layered possibility exists, involving fields that did not drive the great expansion but merely watched it happen. These are the spectator fields. In the simplest model of inflation, a single field, the inflaton, is the star of the show, its energy driving the exponential stretch of space, but the early universe was likely far more crowded. Other quantum fields related to other forces or particles would have been present as well. They were spectators riding along in the inflating space but not providing the primary energy for the expansion itself. You can think of it like a vast, rushing river, the inflaton field. Floating on that river are other objects, logs and leaves. These are the spectator fields. They are carried by the current, but they have their own properties and can interact in their own ways. During the frantic period of inflation, these spectator fields were not idle. As space stretched at a breakneck pace, these fields were subjected to extreme conditions. They could have experienced their own quantum fluctuations, just like the inflaton. More intriguingly, they could have undergone their own instabilities or sudden phase transitions, independent of the main event. Imagine one of those floating logs suddenly cracking in the cold, or a leaf freezing and shattering. These are localized events on the spectator field, but here is the crucial part: these events are not isolated. The spectator field is coupled to the main inflaton field, connected through the fundamental laws of physics. So when a spectator field shudders or shifts phase, it gives a tiny kick to the inflaton field itself. It creates a small perturbation, a hiccup in the smooth roll of the primary driver of the universe's expansion. And in the hypersensitive environment of inflation, where quantum effects are blown up to cosmic size, that tiny kick is magnified to an astronomical scale. The perturbation in the inflaton field translates directly into a perturbation in the fabric of space-time. This creates an additional, secondary source of gravitational waves layered on top of the primary background from the standard inflationary stretch. The signature of these waves would be distinctive because they come from specific, triggered events within spectator fields. They could produce features in the gravitational wave spectrum, like specific peaks or dips at certain frequencies. It would be like listening to a symphony and hearing not just the continuous string section, but the occasional, distinct strike of a triangle or the roll of a snare drum added on top. Detecting such features would be a revelation. It would tell us that the early universe was not a one-field show, but a complex arena where multiple quantum actors interacted. It would give us a direct probe into the particle physics of the highest energies, revealing fields and interactions that are completely invisible to us today, whose only remaining trace is a faint, patterned ripple they left on space-time over 13 billion years ago. The spectators, it turns, may have left the loudest clues. The spectator fields were not the only actors capable of stealing the scene. Another possibility emerges from the very forces that bind our universe together, the fundamental gauge fields. These are the fields that give rise to the forces we know, like electromagnetism. In the calm of today's universe, these fields are quiet and stable. But in the extreme, stretched thin environment of the early cosmos, they could have been awakened into a state of pure, chaotic fury. This is the theory of gauge field production. To grasp it, we need to understand a strange concept called a tachyonic instability. Normally, a field sits comfortably at its lowest energy state, like a ball resting at the bottom of a valley. But under certain conditions, a field can find itself perched on a hilltop in a so-called false vacuum. This is an unstable, high-energy configuration. The slightest nudge will send it rolling violently downhill. In the physics of the very early universe, the rapid expansion of space itself can provide that nudge, effectively turning a once stable gauge field into a tachyon, a state with imaginary mass that wants to run away to grow exponentially. Once this instability is triggered, the field goes wild. It does not oscillate gently like the action. It erupts. Patches of space become dominated by incredibly strong, chaotic configurations of this primordial force field. Think of it as a cosmic lightning storm, but instead of electricity flashing through air, it is the raw force of electromagnetism or another gauge field knotting and whipping through the fabric of space itself. These fields would have possessed immense energy density, and their dynamics would have been violently turbulent. They would have twisted, collided, and recoiled upon themselves. And here is the key: anytime you have a massive amount of energy moving in a non-uniform, asymmetric way, you generate gravitational waves. A calm, uniform sea of energy produces no ripples. But a raging, storm-tossed ocean of force fields absolutely does. The churning of these amplified gauge fields would have acted as an extraordinarily efficient gravitational wave engine, pumping out ripples in space-time with tremendous power. The signal from such an event could be dramatically stronger than the subtle hum predicted by the simplest models of inflation. It would be less like a distant whisper and more like a resonant shout etched into the cosmos. For scientists building the next generation of gravitational wave observatories, this is a thrilling prospect. A signal this loud would stand out clearly from the cosmic noise, making it potentially far easier to detect than the faint inflationary background. Finding it would open a direct window into the behavior of fundamental forces under conditions of energy and density we could never hope to recreate in a laboratory. It would reveal that the universe's infancy was not just a period of smooth expansion, but also a tempestuous era where the very forces of nature ran amok, and in their frenzy, they literally shook the foundations of reality, leaving behind a loud, unmistakable tremor for us to discover. That explosive awakening had a name, and it was not a gentle process. The end of inflation did not lead directly to the calm, expanding fireball we often picture. Instead, the universe entered a period of sheer pandemonium known as reheating. For a fleeting moment, the inflattened field, the engine that had driven the exponential expansion, was still holding a colossal amount of energy locked within itself. The universe was vast but cold and empty, a stretched-out void. Then the field began to decay. It did not fade quietly, it collapsed, and in doing so, it unleashed all of its pent-up energy in a catastrophic cascade. This was the true moment the Big Bang's famous fireball was born. That energy flooded into the universe, violently populating it with a seething, ultra-hot plasma of every fundamental particle and force. Reheating was the universe's explosive ignition. Picture the moment a dam holding back an entire reservoir suddenly shatters. The water does not flow out smoothly. It erupts in a chaotic, churning, roaring deluge that crashes into the valley below, throwing up spray and creating violent whirlpools. Reheating was that deluge, but the water was raw energy and the valley was the entire cosmos. This was not a smooth transition. The decay of the inflattened field was uneven and turbulent. In some regions, it might have decayed faster, in others slower. This created immense density contrasts and pressure waves rippling through the newborn plasma. Particles collided with unimaginable force, annihilating and recreating in a frenzied storm. Within this maelstrom, physicists speculate that strange, stable structures could have formed, knots of energy called solitons. Think of them as permanent waves in the particle soup, self-reinforcing ripples that refuse to dissipate. These solitons would have been massive, potentially containing the energy of stars, and as they moved and interacted in the turbulent medium, they would have been gravitational powerhouses. Every collision, every swirling vortex in this primordial chaos was a source of gravitational waves. The reheating era would have generated a cacophony of space-time ripples, a distinct chorus layered on top of the older inflationary hum. Because reheating was a relatively brief but intensely violent event, its gravitational wave signature could be very specific. It might appear as a noticeable chirp or a bump at a particular frequency range in the overall background, a sharp spike in the data telling us the exact moment the universe truly caught fire. Detecting that chirp would be like finding the fossilized sound of the first thunderclap after a long silence. It would pinpoint the instant the cold, inflated void transformed into the hot, dense, particle-rich cosmos that would eventually give rise to everything we see. The first space-time ripples might therefore carry not just the signature of the stretch, but the unmistakable crash of the universe's explosive birth into light and matter. While cosmic strings are one-dimensional scars, the universe's violent cooling could have left even more dramatic imprints. There is a possibility that two-dimensional defects formed vast, sheet-like structures known as domain walls. Picture the universe's phase transition like a field of grass freezing over on a cold morning. As it freezes, the ice crystals form with random orientations. Where two differently oriented crystals meet, a boundary line forms. Now imagine that process happening in 3 dimensions, with the crystals being different vacuum states of the universe itself. Where these different states met, they could have created not lines, but immense continent-spanning sheets of trapped energy, walls in the very structure of reality. A stable domain wall would be a cosmic disaster. Its sheer gravitational influence would warp the large-scale structure of the universe in ways we simply do not observe. The fact that our cosmos looks uniform tells us that if domain walls ever existed, they could not have lasted. They must have been unstable, destined to decay. And that decay is where our story of gravitational waves truly ignites. These walls, thinner than a single atom yet potentially stretching across vast reaches of the early cosmos, would have been under immense tension, like cosmic membranes stretched to their limit. They would have vibrated, twisted, and developed holes. Once a hole formed, the tension would have pulled it wider and wider, causing the entire sheet to unravel and evaporate in a flash of energy. The annihilation of such a massive structure, a two-dimensional defect dissolving into pure radiation, would have been a gravitational cataclysm. It would have sent a powerful, sharp burst of ripples through the surrounding space-time. Because domain walls are two-dimensional, their decay dynamics are different from oscillating strings. The signal they produce could be very distinctive, potentially contributing a strong, high-frequency component to the primordial gravitational wave background. It would sound less like a continuous hum and more like a series of sharp pops or cracks across the cosmos, the sound of reality tearing itself free from these phantom barriers. Finding evidence of such a signal would be breathtaking. It would confirm that the early universe underwent a specific kind of symmetry breaking, one that left temporary, sheet-like monuments to its own turbulent formation. We would learn that the cosmos had to literally tear down its own walls to become the smooth, habitable place we see today, and the echoes of that demolition are still rippling through the void. These domain walls were temporary monuments, but another kind of symmetry once ruled the cosmos, a principle so elegant it promised to unify all forces. This is supersymmetry. It proposes a breathtakingly beautiful structure for reality where every particle we know has a hidden, heavier twin. For every quark there is a squark. For every electron, a selectron. For the photon, a photino. It is a cosmic doubling, a profound mathematical harmony that would solve several of physics' deepest puzzles at once. In a perfectly supersymmetric universe, these particle partners would be identical in mass to their twins, and the forces would be in perfect balance. But we do not live in that universe. We see no selectrons, no squarks. This tells us a fundamental truth. If supersymmetry is real, it was broken. As the fiery newborn cosmos expanded and cooled, it crossed a critical threshold. The perfect frozen symmetry of the highest energies began to thaw. The partner particles, once massless and equal, suddenly gained immense weight, becoming too heavy to be produced in the ordinary collisions of our cooled-down reality. This breaking of supersymmetry was not a gentle shift. It was a catastrophic cosmic event, a first-order phase transition of staggering scale. Think of it as the universe choosing a side. Picture a magnificent, perfectly balanced spinning top. As it slows, the symmetry of its perfect spin becomes unstable. It wobbles, hesitates for an instant, and then crashes decisively onto its side. That crash, that decisive breaking of perfect balance, is what happened to supersymmetry, and such a violent transition does not happen quietly. Bubbles of the new, broken symmetry vacuum would have nucleated and expanded at nearly light speed, colliding and merging. The walls of these bubbles would have been regions of immense energy density, where the fields mediating the transition released their pent-up force. These collisions would have shaken the fabric of space-time with tremendous violence, generating a powerful chorus of gravitational waves. The signature of these waves would be a direct fingerprint of the breaking. Because the energy scale of supersymmetry breaking is theorized to be astronomically high, far beyond the reach of any particle accelerator we could ever build on Earth, the gravitational waves it produced would have a very specific frequency range, one that next-generation space-based observatories are designed to listen for. Detecting that specific hum would be more than just finding the first ripples. It would be the ultimate experimental triumph. It would mean we have used the entire universe as our laboratory, leveraging its explosive infancy to conduct an experiment at energies a quadrillion times greater than the Large Hadron Collider. We would not just hear the birth cries of space-time, we would be decoding the moment reality chose its fundamental shape, the instant the hidden symmetry that might underpin all of physics was shattered, leaving behind a faint, ringing tremor as its only relic. Supersymmetry's breaking was a shattering of perfect balance, but another kind of hidden structure might have trembled in that same primordial dawn. This brings us to the deep geometry of string theory and the mysterious moduli fields. Our reality, according to this framework, is not just the three dimensions of space and one of time we experience. It is a universe with extra, curled-up dimensions, perhaps 6 or 7 of them, wound into shapes so tiny they escape all notice. The properties of our cosmos, the very strength of gravity and the masses of particles, depend on the exact size and shape of these hidden, microscopic dimensions. And what controls that size and shape? They are governed by moduli fields. Think of a moduli field as the cosmic dial for a hidden dimension. One field might control the radius of a curled-up circle, another the angle of a twist, another the overall volume of all the extra space. In the first instance after the bang, these dials were not set. The moduli fields were wild and free, their values fluctuating chaotically. The extra dimensions themselves were unstable, breathing and writhing at the quantum scale. This could not last. For our stable, four-dimensional world to emerge, these fields had to find their resting places. They had to roll down to their lowest energy states and lock into place, a process physicists call moduli stabilization. It is as if the universe had to tune itself, adjusting a vast array of invisible knobs until it hit the precise combination that allowed atoms, stars, and life to exist. But this tuning was not a silent adjustment. As each moduli field rolled down its energy slope to its stable value, it did not just stop, it overshot. It began to oscillate wildly around that final point, like a weight on a spring bouncing back and forth after being dropped. These were not small vibrations. Each moduli field was tied to the geometry of space itself, and its oscillations represented massive shifts in the fabric of reality on a cosmic scale. And as these colossal fields oscillated, they decayed. They shed their immense energy, dumping it into the particle soup of the early universe. That energetic decay, that violent settling of the cosmic geometry, would have been spectacularly loud in gravitational terms. The asymmetric rolling and oscillating of these fields would have shaken space-time to its core, pumping out a powerful background of gravitational waves. The true wonder lies in the signature of those waves, because each moduli field corresponds to a specific feature of the extra dimensions. The frequency and pattern of the gravitational ripples it produces are a direct reflection of that hidden geometry. The waves are, in essence, a spectral fingerprint. Detecting them and decoding their pattern would be like listening to the ringing of a bell, and from the sound alone, being able to deduce the bell's exact shape, size, and material. In this case, the bell is the shape of the extra dimensions. The primordial gravitational wave background could literally contain encoded information about the number of curled-up dimensions, their sizes, and their topological twists, features of reality that are forever beyond the reach of any telescope or particle collider. It would mean that the first tremors of the cosmos are not just a record of its explosive birth, but a detailed blueprint of its full, higher dimensional architecture. We would be hearing the universe tune itself into existence, and in that ancient hum, we might finally read the hidden dimensions written into the foundation of everything. While moduli fields were tuning the hidden dimensions, the universe itself was a roaring inferno of a different kind. Forget quantum fields and symmetry breaking for a moment. The sheer, raw heat of creation may have been loud enough to shake space-time on its own. This brings us to a more fundamental, almost primal source for those first ripples: thermal gravitational waves. In the first instance, the cosmos was not just a place of exotic fields, it was a particle furnace of unimaginable intensity. A seething, opaque plasma so dense and hot that particles like quarks, gluons, and electrons were not just floating around, they were screaming through the chaos, colliding with energies that make our largest particle accelerators look like child's toys. In this primordial soup, every single interaction was a violent event. Particles were not just bouncing off each other, they were being created and annihilated in a constant, frenetic storm. And here is the crucial point: gravity is universal. It does not just come from massive objects like stars or black holes. According to Einstein's theory, any form of energy and momentum can generate gravitational waves. So, every time two high-energy particles in that early plasma smashed together, their collision was not just a flash of light or a spray of new particles. It was also, in an incredibly tiny way, a tremor in the fabric of space-time. Each collision sent out a minuscule gravitational ripple. Individually, these ripples were vanishingly small, utterly insignificant. But there were quadrillions upon quadrillions of such collisions happening every second, everywhere, throughout the entire volume of the young universe. This creates a cacophony, a background hiss of gravitational noise generated by pure, chaotic thermal motion. Think of a vast stadium filled with people. One person clapping is a tiny, isolated sound. But when 80,000 people all clap at once, even randomly, it creates a powerful, continuous roar. The early universe was that stadium, and every particle was clapping. This thermal gravitational wave background would be the universe's most fundamental noise floor. It is the whisper of the cosmos's own heat, the sound of its most basic constituents jostling in the furious density of their youth. Unlike the distinct patterns from inflation or phase transitions, the thermal background would likely be a smoother, broader spectrum hum. Its properties would directly tell us about the temperature and the particle content of the universe at its hottest, most energetic phase. Detecting this specific hum would be like placing a stethoscope against the universe's first fiery heartbeat. It would confirm that gravity itself is woven into the fabric of every interaction, no matter how small, and that the simple, searing heat of the Big Bang left its own unique tremor echoing through the ages, a baseline murmur beneath all the other, more dramatic cosmic events. The stadium roar of thermal noise was not the only possibility for that early cosmic hum. There exists another elegant twist on the inflationary tale, one where the main star of the show hands off its most critical role to a supporting actor. This is the Curvaton scenario. In the standard story, the inflaton field does two monumental jobs. First, it drives the exponential expansion of space. Second, its own quantum fluctuations are stretched to become the seeds for all cosmic structure. But what if those two jobs were performed by two different fields? Enter the Curvaton, a secondary quantum field that existed alongside the inflaton during the universe's frantic stretch. Think of the inflaton as a mighty engine, its sole purpose to violently and rapidly expand the stage of reality. It does this job perfectly, but it is quiet and smooth. The Curvaton, meanwhile, is a passive spectator on that stage, a field that does not drive the expansion but simply rides along. Its role is subtler. It carries within it the potential for structure. While the inflaton stretches space, the Curvaton field also experiences quantum fluctuations. Because it is a different field with different properties, these fluctuations have their own unique character. Then, after inflation ends and the inflaton field has decayed away, the Curvaton takes center stage. As the universe enters its next phase, the Curvaton field begins to oscillate around its minimum, eventually decaying into the hot plasma of particles. But as it decays, it performs a magic trick. it converts its own unique pattern of quantum fluctuations into actual physical density variations in the cosmic soup. In this model, the slight over-densities that eventually collapsed into galaxies were not imprinted by the inflaton, but by the curvaton. This is a profound shift in the narrative of creation. It means the blueprint for everything we see, stars, galaxies, clusters, came not from the primary force that shaped the cosmos, but from a secondary, almost hidden field. And just as the inflaton's fluctuations generated gravitational waves, so too would the curvatons. As the curvaton field oscillated and decayed, its uneven distribution of energy would have shaken the fabric of space-time, producing its own distinct spectrum of primordial ripples. The signature of these waves could be markedly different. The tilt of the spectrum, which describes how the strength of the waves changes with frequency, or their overall amplitude, might not match the predictions of simple, single-field inflation. A future detection that deviates from the standard inflationary template could therefore point directly to this elegant handoff. It would tell us that the universe's structure is not a direct imprint of the expansion mechanism, but the legacy of a quieter, more subtle field that waited patiently in the wings before stepping forward to sketch the grand design of the cosmos onto the blank slate inflation provided. The curvaton's quiet handoff shows how subtle fields can shape reality, but some theories propose that the early universe flirted with states that defy our basic understanding of physics itself. Among these is the profoundly strange idea of ghost condensation. To grasp it, we need to revisit a fundamental concept, kinetic energy. For anything in our everyday world, kinetic energy is positive. A rolling ball has it, a flowing river has it. It is the energy of motion. In the equations of physics, this positive energy is what keeps systems stable. It acts as a kind of anchor. But ghost condensation dares to ask, what if a field in the infant cosmos had negative kinetic energy? It is as if this field's very motion, its vibration, subtracted energy from the system instead of adding it. This is not just an exotic idea, it is a theoretical state that seems to turn physics on its head, a ghost in the mathematical machinery of the universe. In such a phase, the field is said to be a ghost condensate, and like the name implies, it is an unstable, spooky configuration. Negative kinetic energy creates a powerful instability, a kind of anti-friction that causes any tiny perturbation, any slight unevenness in the field to grow explosively rather than dampen out. Now link this to the fabric of space-time itself. In the early universe, space-time would have been rippling with tiny metric perturbations, minuscule wrinkles in its geometry from quantum effects or other processes. Under normal circumstances, many of these wrinkles would simply fade away as the universe expands. But if a ghost condensate field was present, it would have acted like a cosmic amplifier on steroids. Those tiny, insignificant wrinkles in space-time would have been fed by the condensate's negative energy. They would not just persist, they would be violently amplified, growing from quantum whispers to cosmological roars in a startlingly short time. The result would be a powerful burst of low-frequency gravitational waves. Because the amplification is so efficient and rapid, the signal could be exceptionally strong, a dominant feature in the gravitational wave background at very long wavelengths. This is a theory that truly tests the limits. It pushes general relativity into a regime where our trusted equations might break down, or where new physics must step in to prevent runaway catastrophes that would tear the universe apart. The very possibility of ghost condensation forces us to confront the deepest questions about what forms of energy and matter were permissible in the first moments. Detecting a gravitational wave signal with the specific characteristics predicted by this model would be more than a discovery, it would be a revolution. It would mean that the newborn cosmos passed through a phase that was, by our current standards, physically unnatural, a fleeting era where the rules of motion inverted and the ghosts in the fields left an indelible, booming echo in the structure of space itself. Einstein's theory of relativity has reigned supreme for over a century, the bedrock of our understanding of gravity. But to hear the universe's very first whispers, we may need to step outside it entirely. This brings us to Horava Lifshitz gravity, a radical proposal born from the struggle to marry gravity with quantum mechanics. In Einstein's universe, space and time are woven together into a single, inseparable fabric, space-time. This elegant symmetry is beautiful, but it creates immense mathematical headaches when trying to describe the quantum frenzy of the Big Bang. Horava Lifshitz gravity dares to ask a shocking question: what if that perfect marriage is only an illusion that emerges later? What if, at the highest energies in the universe's first moments, space and time were not partners but separate entities playing by different rules? In this theory, time is given a privileged, absolute status, while space is allowed to have properties that change with scale. It is as if the cosmic fabric, under extreme magnification, reveals itself not as smooth silk, but as a woven grid where the warp and weft behave independently. This technical shift has a breathtaking consequence. It makes gravity amenable to quantum treatment in the early cosmos, potentially solving problems that have stumped physicists for generations. For our story of the first ripples, the implications are profound. If Horava Lifshitz gravity is correct, then the infant universe did not expand in the smooth, relativistic way we've always assumed. Its growth would have been anisotropic, meaning different directions in space could have stretched at different rates. The dynamics of that hyper-chaotic expansion would have been unlike anything in standard cosmology. And whenever you have a violent, asymmetric stretching of the very fabric of reality, you generate gravitational waves, but these would not be the standard inflationary ripples. They would carry the distinct imprint of a universe where time and space were once divorced, a unique spectral signature woven into their frequency and polarization. Detecting that specific pattern would be nothing short of revolutionary. It would be direct evidence that Einstein's sublime geometry is an emergent phenomenon, a later stage harmony that settled over the cosmos as it cooled. We would learn that the deepest foundations of reality are not a unified space-time continuum, but something far stranger, a place where time was once a master and space its turbulent subject. The first space-time ripples could therefore be a misnomer. They might instead be the tremors from the moment space and time finally stitched themselves together into the single fabric we call home. Einstein's geometry might be an emergent harmony, but what if the singularity itself was never real? Loop quantum gravity offers a breathtaking escape from the infinite density of the Big Bang, replacing it with a cosmic rebound. In this framework, space is not a smooth continuum, but a woven fabric of tiny, finite loops, a granular quantum structure. This granularity changes everything about the beginning. There is no singular point of infinite density because the loops cannot be squeezed beyond a certain limit. Instead, picture a universe before ours, vast and ancient, slowly contracting under its own gravity. As it shrank, the density soared, but instead of collapsing into a meaningless singularity, it reached a maximum possible density, a quantum wall. At that wall, the repulsive force generated by the granular geometry of space itself became overwhelming. The contraction halted, reversed, and the universe bounced. That rebound is what we call our Big Bang. Our expanding cosmos was born not from nothing, but from the ashes of a previous cosmic cycle. This is the big bounce. Now, consider the gravitational waves traveling through that transition. In the contracting phase, the universe would have been filled with space-time ripples from the violent events of its late history, colliding black holes, churning plasma, the final acts of a dying cosmos. As space contracted, those waves would have been squeezed, their wavelengths shortened. Then came the bounce, a moment of extreme quantum gravity where the very fabric of reality was rewoven. The granular nature of space at that instant would have acted like a filter on those gravitational waves. The very longest wavelength ripples, those whose physical size was larger than the fundamental quantum grains of space, could not pass through unchanged. They would have been scattered, dampened, or even partially erased by the discrete structure of reality. The result, a primordial gravitational wave background with a distinct signature, a suppression, a noticeable dip in power at the very longest wavelength. It would be as if the lowest notes of the cosmic symphony were muted by the bounce. For cosmologists, searching for this suppression is like looking for the fingerprint of quantum space-time itself. Detecting it would achieve two monumental things at once. First, it would provide direct evidence that our universe is cyclical, that we are living in one chapter of an endless story of cosmic death and rebirth. Second, and perhaps more profound, it would be our first experimental proof that space itself is quantized, that at its heart, reality is woven from tiny, indivisible threads. The first ripples we hear could carry the quiet imprint of the loom that wove them, revealing not just how our universe began, but what it is truly made of. That quantum loom of loop quantum gravity weaves a single universe, but what if our cosmos is just one thread in an infinite tapestry? The inflationary multiverse theory takes the idea of cosmic inflation and runs with it to a staggering conclusion. If a single patch of space can inflate to become our entire observable universe, what stops the process from happening elsewhere over and over again? The leading idea suggests that inflation, once started, is eternal. In some regions it ends, creating stable pocket universes like bubbles forming in a vast boiling sea. Our universe is one such bubble, a localized region where inflation stopped, allowing for stars, galaxies, and us to form. But outside our bubble, the meta-universe, the void between bubbles, continues inflating eternally, spawning an endless froth of new cosmic domains, each with potentially different physical laws and constants. This is the multiverse in its most literal sense. Now, imagine two of these bubbles, each an entire universe with its own Big Bang history, expanding through the hyper-fast inflating background. Their walls, the boundaries where inflation stopped, are like shock fronts moving at nearly light speed. Over cosmic eons, two such expanding bubbles can drift toward each other and eventually collide. The moment of impact would be a cataclysm of almost biblical scale, a clash of entire realities. The collision would not merge the universes into one. Rather, it would create a localized, incredibly energetic scar on the boundary wall of each bubble. That collision zone would be searingly hot, imprinted with a complex anisotropic pattern, a cosmic bruise where the laws of physics from two separate worlds briefly met and interacted. Such a violent, asymmetric event would, without a doubt, send powerful gravitational shockwaves rippling through the interior of each bubble universe. For us, inside our pocket, this would manifest as a very specific kind of primordial gravitational wave signal. It would not be the uniform background hum from our own inflation, but a directed, localized burst coming from a specific direction on the sky, with a distinct polarization pattern that screams anisotropic event. The waves would carry a fingerprint of the collision's geometry and, astonishingly, information about the other universe. They might encode data about the energy of its vacuum, the nature of its inflation, or even fundamental constants different from our own. While these signals are predicted to be very faint, stretched and diluted by our universe's subsequent expansion, their potential detection would change everything. It would be the first empirical evidence for the existence of other universes. We would no longer be theorizing about a multiverse in the abstract. We would have a direct measurement, a tremor in our space-time that began not in our cosmos but from a clash with another. Finding such a signal would mean our universe bears a scar from a long-ago encounter with a stranger reality, and the echo of that encounter is still washing over us, a whisper from beyond the bubble. The beauty of a simple idea is its testability, and cosmic inflation offers a remarkably clean prediction. For the most straightforward models, the ones driven by a single, slowly rolling field, there exists a mathematical lockstep between two key properties of the primordial gravitational waves. The first is their overall strength, known as the tensor amplitude. The second is how that strength changes across different frequencies, a property called the tensor spectral tilt. In these simple models, these two numbers are not independent. They are linked by a precise equation known as the consistency relation. It is a fingerprint of minimal inflation. A future detection of the primordial gravitational wave background would give us both of these numbers for the very first time. We could plug them into the equation and see if they match. If they do, it would be a monumental triumph, a powerful confirmation that the universe's explosive birth was guided by an elegant single-field process. But what if the numbers do not match? What if the measured strength and tilt of those ancient ripples violate the consistency relation? That result would be just as revolutionary, but in a different way. It would act like a cosmic veto, decisively ruling out an entire universe of simple, elegant inflationary models at once. The clean, minimal story would be wrong. Such a violation would be a clear signal from the dawn of time, telling us that the early universe was far more complex than we had hoped. It would force cosmologists to abandon the simplest pictures and embrace the exotic. Suddenly, every one of those wild alternatives we have explored would move from speculative possibility to front-runner status. A violation could point directly to multi-field inflation, where the curvaton or spectator fields we discussed left their mark. It could be evidence for a dramatic phase transition, the shattering of supersymmetry, or the violent dynamics of gauge fields running wild. It might even hint at something beyond standard inflation entirely, like a bounce from loop quantum gravity or a collision in a higher dimensional bulk. This is why the tensor spectrum consistency relation is not just another measurement, it is a cosmic litmus test. The first ripples we detect will not only be a sound from the beginning, they will be a data set, a set of numbers we can hold up to the light of theory. And depending on what those numbers say, they will either confirm our most elegant dream of creation or send us headlong into a labyrinth of far stranger, more intricate possibilities, where the universe's first act was a drama with many players, not a solo performance. The consistency relation is a clean mathematical line, but the early universe was a place of messy, dynamic feedback. One of the most intricate possibilities involves a process that turns the very fabric of space-time into an engine for its own disturbance. This is the particle production back reaction. To see it, we must return to that frantic inflationary stretch where space was expanding faster than light. In the seething quantum vacuum, virtual particle-antiparticle pairs constantly flicker into existence, borrowing energy from the void only to annihilate and repay the debt an instant later. It is a ceaseless, microscopic dance, but in the violently stretching geometry of inflation, something profound can happen. If space expands rapidly enough, it can pull these virtual pairs apart before they have a chance to annihilate. It is as if two dancers holding hands are suddenly standing on opposite sides of a room that is doubling in size every fraction of a second. Their connection is severed. In that moment, the borrowed energy cannot be returned. The virtual particles are ripped from the vacuum and promoted to real, lasting entities. Inflation becomes a prolific particle factory, flooding the nascent cosmos with matter and radiation from nothing but the stretching of space itself. This is where the story deepens. All these newly created particles carry energy and momentum. They are not a smooth, uniform mist. They form clusters and streams, creating uneven patches of density and pressure in the expanding cosmos. And gravity is exquisitely sensitive to such irregularities. Every lump, every swirl in this newborn particle soup exerts a tiny gravitational pull on the very geometry of space-time around it. This gravitational influence is the back reaction. The particles born from the stretching of space now push back on that space, subtly warping and wrinkling it. That warping is not silent. As these density contrasts move and evolve, they act like billions of tiny paddles churning the fabric of reality, generating secondary gravitational waves. This sets up a potential feedback loop of astonishing complexity. The initial inflationary expansion creates particles. Those particles distort space-time, creating gravitational waves. But those waves themselves are ripples in geometry, and in the ultra-energetic environment of the early universe, they too can interact. They can scatter off each other, or their oscillating energy can catalyze the production of even more particles. Waves beget particles, which beget more waves in a cascading dance of mutual creation. The result could be a gravitational wave background far richer and more textured than the simple hum predicted by models that ignore this back reaction. It might carry specific resonances, bumps, or kinks in its spectrum, a complex fingerprint of this self-reinforcing cosmic conversation. Detecting such a non-standard signal would reveal an early universe that was not a silent, smooth expansion, but a boiling, interactive cauldron where space, particles, and gravity were locked in a fierce, generative dialogue, each constantly shaping and being shaped by the others in the first moments of everything. That intricate feedback loop between particles and waves reveals a cosmos in conversation with itself. But what if the very rules of the conversation were skewed from the start? This leads us to a subtle yet profound modification of Einstein's masterpiece known as Chern-Simons gravity. In our everyday experience, the universe appears ambidextrous or symmetric. The laws of physics do not favor left over right. This symmetry is called parity. Drop a spinning ball, and its mirror image would spin the opposite way, but both are equally valid according to gravity as we know it. Chern-Simons gravity dares to suggest that in the extreme energies of the early universe, this was not true for gravity itself. In this theory, a new universal field, often called the axion-like field we met earlier, does not just fill space, it engages in a direct, intimate dance with the very geometry of space-time. It couples to gravity through a mathematical term known as the Chern-Simons term. This coupling is not a gentle handshake, it is a specific twist that treats left-handed and right-handed rotations differently. To understand this, think of gravitational waves not just as ripples but as waves that can spin. As a gravitational wave travels toward you, it can rotate in two distinct ways, like a corkscrew spinning clockwise or counterclockwise. These are its two possible polarizations, left-handed and right-handed. In standard Einstein gravity, both polarizations travel identically at the same speed with the same strength. They are perfect mirror twins, but in Chern-Simons gravity, the coupling to the new field changes the game. The field acts like a cosmic filter, making space-time itself optically active for gravity. One-handedness of wave might travel slightly faster or be amplified, while the other is slowed or dampened. This effect is called gravitational birefringence. Now project this back to the universe's first moments. If this chiral field was active during inflation or another primordial process, the gravitational waves generated would have been born with this handedness imprinted on them. The waves would not be an even mix of left and right. Instead, there would be a net chirality, a preference for one spinning direction over the other, woven into the very fabric of the primordial ripple. This is not a small detail, it is a fundamental violation of parity in the force of gravity. It would mean that at the deepest level, the cosmos has a preferred handedness, a subtle twist in the laws that govern the shape of reality. The stunning consequence is that this chiral signature would survive, frozen into the gravitational wave background that reaches us today. By carefully measuring the polarization of those ancient ripples, scientists could detect this imbalance. Finding it would be a discovery of staggering implication. We would have direct evidence that gravity itself is not the perfectly symmetric force we assumed, but that it carried a hidden bias from the moment of creation. It would point unequivocally to new physics beyond Einstein, revealing a universe that chose a direction in its very first tremors, a direction we might still be able to trace in the spin of echoes from the dawn of time. That subtle twist in gravity's handshake hints at an even deeper strangeness woven into the fabric of reality. At the universe's absolute birth, the very stage on which events unfold might have dissolved into a fundamental ambiguity. This is the realm of non-commutative geometry, a concept where the order of operations defines reality itself. In our everyday world and in all of classical and quantum physics, it does not matter what order you measure certain properties. You can note an object's position and then its momentum, or its momentum and then its position, and you will get the same combined result. The measurements commute. But in the searing forge of the Planck epoch, some theories suggest this basic rule broke down. Space and time themselves might have become non-commutative. Imagine the coordinates of an event, its here and now, no longer being simple numbers. Instead, they become more like mathematical objects that refuse to switch places neatly. In this bizarre regime, measuring the position of a quantum fluctuation in one direction and then another might yield a different result than if you measured them in the reverse order. The sequence of events becomes inherently fuzzy. There is no sharp before and after at the smallest scales, only a probabilistic cloud of potential sequences. This is not just a philosophical curiosity, it is a concrete prediction from several approaches to quantum gravity, including some string theory landscapes and certain models of loop quantum gravity. Now, link this profound fuzziness to the moment of cosmic inflation. As we have discussed, inflation takes microscopic quantum fluctuations and stretches them into cosmic seeds. But if the geometry of space-time was non-commutative during that critical stretching period, the process would have been altered in a subtle but detectable way. Quantum jitters that were being amplified were not the clean, well-ordered fluctuations of a classical stage. They were born from a froth where here and there were fundamentally blurred. As inflation stretched this fuzzy quantum foam, it would have imprinted its unique statistical character onto the resulting gravitational waves. In standard models, the distribution of these waves across different frequencies is Gaussian, meaning it follows a familiar bell curve-like pattern of randomness. It is the cosmic equivalent of static, but non-commutative geometry would twist that static. It would introduce specific correlations between waves of different wavelengths, creating a pattern that deviates from pure randomness. This deviation is known as non-Gaussianity. It would be a subtle signature, a specific, intricate pattern woven into the statistical tapestry of the primordial gravitational wave background. Finding it would be nothing short of revolutionary. It would be direct observational evidence that at the highest energies, the universe operates under a completely different logical framework, where the very concepts of location and sequence are derived from a deeper, non-commutative algebra. We would not just be detecting waves from the early universe, we would be reading the first operational manual for reality, written in a language where order itself is a quantum variable. The first ripples could carry the faint statistical echo of a time when here and there were still arguing about which came first. The smooth, cold expansion of standard inflation is a powerful story, but it might be missing a crucial source of heat. For decades, the dominant picture has been one of cold inflation, where the inflatoned field drives expansion while isolated from the rest of the cosmos, a solo performer on a frozen stage. Yet an intriguing alternative suggests the early universe was never that lonely or that cold. This is warm inflation. In this scenario, the inflatoned field is not an isolated entity. From the very beginning, it is strongly and constantly coupled to a thermal bath of radiation. Think of it not as a single ice skater gliding across a pristine rink, but as a dancer moving through a crowded, heated ballroom. The dancer is still leading, but the heat and the jostle of the other dancers fundamentally change the performance. This constant interaction means the inflattened field is continuously dissipating its energy, dumping heat into the surrounding particle soup even as it drives the exponential stretch of space. The universe inflates, but it does so while staying warm, perhaps even hot. This changes everything about the source of the cosmic seeds. In cold inflation, the structures of our universe come from quantum fluctuations in the solitary inflattened field stretched to cosmic size. In warm inflation, the dominant perturbations are not these pure quantum whispers. Instead, they come from thermal fluctuations. The inflattened field is constantly buffeted by the heat of the radiation bath it is coupled to, like a reed vibrating in a hot wind. These thermal jitters, born from the chaotic motion of particles, are then stretched by inflation to become the primordial density variations. The gravitational wave story shifts dramatically here. Thermal fluctuations are fundamentally different from quantum fluctuations in how they generate ripples in space-time. The result is a prediction that the spectrum of primordial gravitational waves from warm inflation is typically much weaker than in the standard cold models. The tensor-to-scalar ratio, that key measure of gravitational wave strength, could be suppressed by several orders of magnitude. This is not a minor adjustment. It is a potential explanation hiding in plain sight. If warm inflation is correct, the reason our most sensitive experiments have not yet detected the first space-time ripples might be beautifully simple. They are just far quieter than we have been listening for. The universe's opening act may not have been a solo in a silent hall, but a vibrant, heated ensemble piece, and its gravitational echo is the soft hum of that collective warmth, a whisper so faint we are only now learning how to truly listen. The slow, graceful roll of the inflattened field is a cornerstone of our standard cosmic story, but it is not the only possible rhythm for creation. A fascinating variation suggests the field did not crawl but charged. This is constant roll inflation, a model where the inflattened field maintains a faster, steady pace down its energy slope, like a ball rolling down a long, steep incline with unwavering speed. This simple change in velocity rewrites the dynamics of the universe's first moment. In the slow roll picture, the field's motion is gentle enough to allow the exponential expansion to sustain itself, smoothing the cosmos while delicately imprinting quantum whispers. But a constant, faster roll introduces a new kind of tension. The field's kinetic energy becomes a more dominant player, creating a different interplay between the energy driving the expansion and the energy of the field's own motion. This heightened kinetic energy does not just fade into the background, it actively sculpts the gravitational wave background in a unique way. The more vigorous, steady motion of the field stirs the fabric of space-time more aggressively as it travels. This can lead to a pronounced enhancement in the production of gravitational waves at particular frequency bands. Instead of a smooth, featureless spectrum, constant roll inflation could imprint a distinct peak or a specific, tilted pattern onto the primordial hum. It would be like listening to a steady drumbeat and hearing a louder, resonant thump every few measures. For cosmologists, detecting such a feature would be a direct clue to the inflattened's gate. A clean peak in the data would point decisively to a period where the inflationary engine was not idling in a slow cruise, but was engaged in a higher gear, driving the expansion with a more forceful and consistent push. This would tell us that the mechanism behind the universe's great stretch had a different character, one where the field's momentum was as important as its potential energy. It opens a window into the precise shape of that primordial energy landscape, revealing not just that inflation happened, but exactly how its prime mover behaved on the journey. The first ripples we hear could carry the rhythmic signature of a field in a hurry, a steady cadence from an era when the cosmos expanded under a different, more driven tempo. The slow, steady roll of inflation is not the only way to build a cosmos. A radical alternative suggests the universe never needed a singular, explosive beginning at all. This is the Galilean Genesis scenario, a model that sidesteps the Big Bang singularity entirely by proposing a universe that was eternal, static, and nearly empty in its infinite past. Picture not a fireball but a quiet, featureless void, a state known as Minkowski space. In this profound stillness, a special quantum field, known as a Galilean field, begins to stir. Unlike the inflaton, this field does not drive a frantic, exponential expansion. Instead, it initiates a process of gradual, accelerating genesis. The field's unique dynamics act as a cosmic engine that slowly, persistently coaxes the universe out of its eternal slumber. Space itself begins to expand, but from a whisper, not a bang. It is a gentle awakening from a timeless sleep. In such a slow-start universe, the conditions for generating primordial gravitational waves are dramatically different. The violent, rapid stretching of inflation acts like a magnifying glass for quantum jitters, blowing them up into cosmic ripples. But in the Galilean Genesis, the early expansion is much more sedate. There is no period of hyper-fast stretching to amplify those microscopic fluctuations to the same immense scales. Consequently, the production of gravitational waves, especially at the very largest wavelengths that correspond to the earliest moments, is highly suppressed. It could even be nearly zero. This creates a stark, testable prediction. While inflation typically forecasts a detectable hum of primordial gravitational waves across a broad spectrum, the Galilean Genesis model predicts a profound silence at the largest scales. It is the difference between expecting the roar of a waterfall and hearing only the faintest rustle of leaves. For cosmologists, a future observation that finds no evidence of these large-scale primordial ripples would be a thunderous result. It would not merely rule out a few inflationary models, it would challenge the entire paradigm of a hot, singular beginning. A null detection could become the strongest evidence yet for a universe that emerged gracefully from eternity, without a bang, without a singularity, through the quiet, persistent work of a field writing its own Genesis story into the fabric of a slowly stirring reality. The cosmos we observe today appears beautifully, profoundly symmetric on the largest scales. Look in any direction, and the grand tapestry of galaxies and cosmic voids looks essentially the same. This cornerstone of cosmology, the assumption of perfect isotropy, is baked into our standard story of inflation. But what if that symmetry was only a final act, a mask that fell into place after the curtain first rose? Theory 29 dares to question this foundational premise. It proposes that inflation itself may have begun with a subtle but crucial imperfection, a whisper of directionality woven into the fabric of the newborn universe. This is the imprint of anisotropic inflation. In the standard picture, the inflaton field is a simple, scalar entity, a single number at every point in space, expanding the cosmos with perfect, democratic uniformity in all directions. But the early universe was likely a far more complex arena. It could have harbored other, more directional actors, like primordial magnetic fields of staggering strength or fundamental vector fields, entities that, unlike scalars, point in a specific direction. Imagine starting inflation not with a perfectly round, smooth ball of energy, but with one that is slightly squashed like an egg. Or picture the inflaton field trying to roll down its energy slope while a powerful, cosmic-scale magnetic field runs through it like a current through a wire, giving the expansion a subtle directional tug. This initial anisotropy would not have lasted long. The incredible exponential stretch of inflation would have rapidly smoothed it out, ironing the cosmic wrinkles to near perfection. But near is the operative word. Some trace of that original directionality could have been frozen into the very first gravitational waves produced. Here is how it works. Gravitational waves are not just ripples, they have a polarization, a specific way they stretch and squeeze space as they pass. In a perfectly isotropic universe, these polarizations are randomly oriented, with no preferred compass direction across the sky. But if inflation began with an anisotropic seed, that seed would have imprinted a subtle bias onto the waves. The gravitational ripples would carry a faint but detectable net polarization aligned with that primordial direction. It would be as if the universe's first shudder had a specific orientation, a cosmic tremor that squeezed space more in one celestial direction than another. Finding such a signal would be a discovery of profound philosophical weight. It would mean the cosmos at its birth was not perfectly featureless and symmetric. It had a grain like wood, a subtle texture that pointed in a specific way. We would have to rewrite our origin story to include this initial cosmic tilt, this forgotten axis of creation. The search for this pattern is not just a hunt for waves, it is a search for the universe's lost compass, a faint arrow in the sky pointing back to the very first instant when direction mattered before symmetry became the rule. Anisotropic inflation hints at a forgotten direction, but there is a deeper, more fundamental crack in our story of creation. It is called the trans-Planckian problem, and it strikes at the very heart of our ability to describe the universe's first moment. To see it, we must follow a single primordial gravitational wave, one of those quantum whispers stretched to cosmic size all the way back to its birth. According to our standard calculations, that ripple began its life with an incredibly short wavelength, far, far shorter than the Planck length. That is a profound issue. The Planck length is the scale at which our trusted laws of physics, Einstein's gravity and quantum field theory, are expected to break down completely, dissolving into the unknown realm of quantum gravity. It is the ultimate edge of our map, yet our origin story confidently tells us that these crucial seeds of cosmic structure were born in a territory our physics cannot describe. It is as if we are writing a biography of someone, and we begin the story with a detailed account of their conception from atoms we have never seen, obeying rules we have never written. This is the trans-Planckian problem. The fluctuations that became everything from galaxies to gravitational waves are traced back to a regime where our equations are meaningless. So, what does this mean for our search? It means the primordial gravitational wave spectrum is not just a signal from the early universe. It is a message from beyond the edge of known physics. The specific pattern of those ripples, their strength across different frequencies, could carry the direct imprint of whatever new laws take over at the Planck scale. For instance, one leading idea is that space itself has a fundamental graininess, a minimum possible length like the pixels on a screen. In such a universe, a wavelength cannot be shorter than this pixel size. This would place a cutoff, altering the very initial conditions for those quantum fluctuations. They would not be born with infinitely short wavelengths, but with a fundamental limit. Another possibility involves modified dispersion relations, where the relationship between a wave's energy and its momentum changes at those extreme scales, like light traveling through a strange, fundamental medium. These new Planck-scale physics would act as a filter on the birth cries of space-time, imprinting a unique signature on the gravitational waves as they are stretched. A bump, a dip, or a specific oscillatory pattern in the spectrum could be the telltale sign. Therefore, when we finally detect that faint hum from the dawn of time, we will be doing much more than cosmology. We will be conducting an experiment in quantum gravity. The gravitational wave background becomes our only possible telescope into that unreachable domain. It offers a chance to read the first chapter of the universe, a chapter written in the language of a theory we have yet to discover, using the one messenger, gravity itself, that was present at the very beginning. The silence we hear or the specific song we find will tell us what lies beyond the edge of all our maps. This staggering array of ideas, from vibrating cosmic strings to colliding universe brains, from the quantum foam's chaos to the silent birth of a Galilean cosmos, reveals something fundamental. Our quest for the first space-time ripples is not a narrow hunt for a single answer. It is the opening of a vast and final frontier in experimental physics. Detecting these primordial whispers would do more than confirm one elegant theory. It would perform a grand cosmic triage, The specific frequency, the amplitude, the polarization pattern of that ancient hum will act as a key, unlocking one door while simultaneously locking countless others forever. A loud, clear signal at certain frequencies could validate cosmic inflation and rule out gentle beginnings. A chiral twist in the polarization would demand new physics like Chern-Simons gravity. Profound silence at the largest scales might point to a universe without a traditional Big Bang. Each possible detection is a scythe, cutting away whole forests of beautiful speculation to reveal the singular, strange shape of our true origin. This is why the search is so urgent and so profound. We are not just listening for a sound, we are building a filter for reality itself, testing the wildest dreams of theoretical physics against the immutable record of the cosmos's first instant. Our tools for this ultimate listen are now taking shape. On the ground, pulsar timing arrays use the precise ticks of dead stars as a galaxy-sized detector, seeking the low-frequency rumble of merging supermassive black holes and perhaps the faintest imprint of the primordial background. In the coming decades, the Laser Interferometer Space Antenna, or LISA, will open a new window from orbit. This constellation of 3 spacecraft, millions of kilometers apart, will sense mid-frequency ripples from the dawn of the first black holes and may finally hear the chorus from cosmic strings or first-order phase transitions. And on the drawing boards are concepts like the Big Bang Observer, a mission designed with one paramount goal: to capture the direct signature of inflation's gravitational waves. These are not mere machines, they are time machines tuned to listen for echoes that have been traveling for over 13 billion years. The quietest sound in the universe is about to be sought with the most ambitious instruments we have ever conceived. So stay curious. The next great discovery in fundamental physics may not come from a tunnel under the Alps, but from the silent space between stars, where a faint, ancient tremor holds the answer to our oldest question. When that ripple is finally found, it will not just shake our detectors, it will reshape our understanding of everything.